Welcome back. In the previous video, we first used only the accelerometer to control our 3D model. As you saw in the first 45 seconds, the model was able to estimate orientation using gravity alone. However, when the sensor was moved quickly, the output became noisy because the accelerometer also measures linear acceleration. After that, we switched to the gyroscope. The movement became much smoother. But since the gyroscope measures angular velocity, we had to integrate its output to estimate the angle. Even a very small bias caused the estimated angle to drift over time. We also demonstrated how adding gyro bias makes this drift even more noticeable. So the question is, can we combine the stability of the accelerometer with the smooth response of the gyroscope? The answer is yes. And that's exactly what we are going to build today using the complementary filter. The idea behind complementary filter is simple. We trust gyroscope for short-term motion because it responds quickly and provides smooth rotation estimates. At the same time, we trust accelerometer for long-term orientation because it uses the gravity as absolute reference and does not suffer from drift. So now let's revise it quickly. You can see that accelerometer is suffering from noise while the gyroscope is suffering from drift. Here we have manually introduced some bias because our gyroscope was calibrated and it was taking long time for drifting. So it is just to show you. Now next see the complementary filter. So here we have applied the complementary filter. Now the motion is smooth and even it is not drifting now. It started drifting. Here it is not drifting. Now as discussed, let's go through the complementary filter code. So actually this is the function which is getting called. So here we are passing AX, AY, AZ, similarly ZX, ZY and ZZ and DT. So first of all, we are calculating accelerometer roll and pitch. So this we had already shown in the previous video. So we will not work on that. Similarly, here we are integrating the gyro data just to get that gyro roll, pitch and yaw. Then we are applying the filter, that is complementary filter, as we had discussed earlier, the equation that is alpha multiplied by angle plus 1 minus alpha multiplied by accelerometer angle, and the first one was the gyro angle. So similarly, it is applied for pitch. We are multiplying the gyro pitch with that alpha and then 1 minus alpha and then accelerometer pitch. Then returning roll, pitch and yaw. You might have noticed something interesting. We applied the complementary filter to roll and pitch, but not to yaw. Why is that? The reason is simple. The accelerometer measures gravity which allows us to determine roll and pitch. However, rotating around the gravity vector, that is yaw, does not change the direction of gravity. As a result, the accelerometer provides no information about yaw. Since the accelerometer cannot correct raw drift, the yaw angle is still obtained only by integrating the gyroscope data. This means yaw will continue to drift over time. So how do we correct yaw drift? For that, we need another sensor, a magnetometer. By measuring the Earth's magnetic field, the magnetometer provides an absolute heading reference, allowing us to correct the yaw angle.